In this video, we're going to finish chapter 7 and find out what happens if we do have forces like friction that take energy away from our system. So we know that in chapter 7, conservation of energy, if we have no friction-like forces, meaning that there is no energy lost from our system, we have equations that we can use, delta K plus delta U equals 0, or the equally good K final plus U final equals K initial plus U initial. So that is the total energy we have at the end is equal to the total energy we have at the beginning. So if we do have some amount of energy leaving the system because of friction or some other force like friction that that takes mechanical energy away, we only have to change these equations slightly. And to introduce this, I'm going to introduce a new term. So we talked about how gravity and spring forces are conservative forces. We're going to explicitly label friction as a non-conservative force. So non-conservative, we're going to abbreviate NC because that's going to come up again. So friction is a non-conservative force. There are other non-conservative forces like air resistance, or if we're talking about fluids, viscosity, things like that can take energy away, take mechanical energy away and turn it into other forms of energy. So if we do have forces like this, these equations change as follows. Delta K plus delta U isn't equal to 0. It is equal to the work done by whatever those non-conservatives are. So WNC, this is the work done by those non-conservative forces. So this would be the work, if we had something sliding on a table with friction, this would be the work done by friction in that situation. All right. We can also rearrange this equation as we've done before, and rearrange it, or actually, we just have to add the non-conservative work to it too. So K final plus U final is equal to K initial plus U initial plus the non-conservative work, the work of the non-conservative forces. So this is still our final energy, this is still our initial energy, and this is how much our energy is changing from initial to final. So this we can kind of think of like a, delta energy that we are, we're adding or subtracting some energy to or from the system. All right, so these are what we're gonna use if we do have friction. And let's, and if we do have work done by a non-conservative force, excuse me, that should be an equals sign. If we do have work done by a non-conservative force, so for example, we have a block that starts with some velocity and ends with no velocity, initial, final. We already know how to analyze this in terms of forces, right? Quick free body diagram for this. We have normal force, gravity, and our kinetic friction that is slowing the block down to a stop. Well, we mentioned this when we talked about friction. Friction always opposes the direction of motion, so work done by friction is always going to have 180 degrees in this theta, which means that the work from friction is always going to be less than 0. So in this equation, this term is always going to be negative, which means that the change in our kinetic energy plus the change in our potential energy is adding up to some negative number. Like one of these might go up and the other might go down, but when we add those changes together, we have to end up with, this amount less energy than we started. So the fact that the work done by friction is negative is important. That's always going to be a negative in this equation. We could have forces that are adding energy to our system, and so therefore we could think of them as a force that doesn't conserve energy because it is adding energy to the system. So for example, we could think about a problem, let's just, no numbers, just conceptual example. Let's say we have our block and it starts with some v equals 0, but there's some force on it, right? So we're pushing this, there's some person who is pushing the block and applying a force to it, an external force. So if we're looking at our, system of one block, it starts with no kinetic energy. It ends with, with some kinetic energy. And so if we think about this in terms of energy conservation, this person is doing work on the block. They're adding energy to that situation. So we could think of this pushing force as doing work that, that is coming from somewhere that we're not accounting for with our potential energy, right? So non-conservative here really means it's not, whatever energy we lose or gain from that is not included in the potential energy. Like gravity and springs have potential energies, but this person pushing the block, they don't have potential energy that we can really discuss in Physics 106. They have chemical energy in the, ATP in their cells or something like that. So since we can account for that, this work is appearing, and so we can kind of think of it as a non-conservative work. This in thinking about situations or in the lab, when this is positive, it's usually coming from some chemical energy turning into mechanical energy, like us pushing a block or an explosion pushing on an object or something like that. All right, so next we're going to do an example of this. So hopefully it'll give you a sense of how we can apply this equation to see what's happening.